Hello everyone, welcome to the class once again. I hope you're all doing good and you're enjoying learning physics with me. I believe that you have seen the last class and you have understood about that there's an excess pressure inside a liquid drop. And this pressure exceeds by an amount 2s by r compared to the pressure outside the liquid drop. Now today we'll go ahead with this concept and we'll learn about what is the excess pressure inside a soap bubble. Now see here, in the last class, first of all, we have seen that there's an excess pressure inside a drop and that excess pressure stands to be 2s by r. If I say this is a liquid drop, it's completely filled with liquid molecules all inside this drop. Now we know that the excess pressure inside this drop will be equal to 2s by r. We all know this. Now let's start with an example. Let's say we have taken a mercury drop. Let's start with an example. We have taken a mercury drop and let's say we are interested to find out what is the amount of excess pressure inside the drop compared to the pressure outside the drop. Now it says that the surface tension of mercury is given as 465 dyne per centimeter. This is what has been provided to us. The surface tension of mercury is given as 465 dyne per centimeter. Now the radius of the mercury drop is given as 2 mm. So we want to find out what is the excess pressure existing inside the mercury drop. So find out the excess pressure inside the mercury drop. So how can we find out that? We all know that the excess pressure existing inside any liquid drop will be given as 2s by r. So simply you have to substitute all the values of the given variables. So substitute here 2, value of s is 465 dyne per centimeter. So 465 dyne per centimeter divided by radius 2 mm. Can we convert it into centimeter? So this will give us 2 into 10 to power minus 1 centimeter. 2 and 2 will be cancelled out. You will be left with 465. This 10 will go up. Now see 10 to power minus 1. If you take it up, it will be 10 to power plus 1. So you will be getting this as 4650 dyne per square centimeter. This is what you are going to get as the excess pressure existing inside the mercury drop. Now you can easily convert the value, you convert the unit in proper SI units also, that you can do on your own. I'm leaving it up to you. You can see this is the excess pressure existing. Now in the same question, suppose it is asked, what is the amount of pressure inside the drop? If the atmospheric pressure is given as 1.013 into 10 to the power 6 dyne per square centimeter. What do I mean to say? Suppose if it's given that, you have to also find out what is the amount of pressure that is existing inside the drop. Amount of pressure inside the drop. Suppose this is asked from you. Then how can you solve such question? Amount of pressure inside the drop, it's given that atmospheric pressure is provided to you as, let's keep it very simple, 1 into 10 to power 6 dyne per square centimeter. This is that has been provided to you. We all know that if the pressure inside is Pi, we all know that if the pressure inside is Pi, so we can write Pi minus P naught. This was 2s by r. That is what we have evaluated. Now Pi will come out to be, that is the pressure inside, is equal to P naught plus 2s by r. Now see here, P naught plus 2s by r. P naught value is the atmospheric pressure, that is 1 into 10 to power 6 plus 2s by r, that already we have evaluated. You can see that its value is 4650 dyne per square centimeter. So plus 4650. I am keeping the units as same, as both have the same unit. So dyne per square centimeter. Now see here, this is quite simple. You can see this can be written as 1.013 0.00465 multiplied by 10 to power 6. We can write that 4650 can be written as 0.004650 into 10 to power 6. It can be written. So we can write that this is 1.00465 into 10 to power 6 dyne per square centimeter. This will be the amount of pressure that will be existing within the mercury drop. Easy question. If you have understood the concepts, you can simply solve this by substituting the values in the formula. Quite simple. Let's go ahead. The next problem, or let's study the next concept. Now I believe that the excess pressure concept would be clear to you all. What is the excess pressure existing within a liquid drop? Next we have, what if we have a bubble? If we have a soap bubble, so let's try to understand excess pressure inside a soap bubble. Excess pressure inside a soap bubble, or inside any bubble you can take. I will take a soap bubble so that you may remember that what kind of drop we are talking about. Now see, you would have made soap bubbles with the toy and you would have played with it. You would have actually blown air through soap solution. You will find that soap bubbles are formed. If you try to observe closely the soap bubbles, how will it look like? You see, it has got two surfaces. One, this is now soap solution will be a thin film. So I'm going to draw a thin film of soap solution. You see why I'm drawing two layers? Just to show you that a soap bubble will be having a soap film. Now see this part that I have shown you here, this part is actually containing the soap solution. That's why I have shown two different layers of soap surfaces that are formed. Now see the white dotted lines that I have drawn, that is actually depicting the soap solution part. This is outside, we have air here, and here also we have air. It's a soap bubble here. Inside also will be having air. Now we are talking about what is the amount of excess pressure inside compared to the outside. Let's say we have pressure here as P0, and let's say we have pressure here as P1, and let's say we have pressure inside the drop as P2. We all know this. Now we all know that the pressure inside the concave surface is in excess, and excess by an amount 2s by r. So we know pressure inside the concave part is in excess. We know pressure inside the concave part is in excess. Pressure inside the concave part is in excess. We all know that. And this excess amount of pressure, this actually exceeds by an amount 2s by r. This is what we know. So we can write P1 minus P0 is equal to 2s by r. Now see, you can think that why are we taking only one radius? Why aren't we not taking two radius? See, this part will be very small. Although I have shown the dimension to be of some finite value, but the soap film will be of a very small molecular layer. So we need not to consider this width. So that's why I have taken P1 minus P0, the radius of this outer part also as r, that has been given here. So P1 minus P0 is 2s by r. Now let me write also, it will be applicable that P2 minus P1 will be 2s by r, because P2, this, now observe this part, this is acting as a concave part for this part. So P2 will be in excess compared to P1 by an amount 2s by r. Let's substitute here. Now add both these, P1 will be cancelled out. You will be left with P2 minus P0. Or what I'm going to do, I'm going to show that this is equation number 1, equation number 2. So if you add 1 and 2, you are going to obtain P2 minus P0 is equal to 4s by r. This time the excess pressure inside a soap bubble will not be 2s by r, it will be 4s by r. This is what you have to remember. It will be 4s by r. See here, because we got two concave surfaces, one here, one here. So the excess pressure that will exceed by an amount that is given by 4s by r. I hope that this concept is pretty much clear to you all. So what do you take note till here? Let me start from the other end. So I believe that you would be pretty much clear about that what is the amount of excess pressure both in the case of a soap bubble and in the case of a liquid drop. So let's go ahead, and these two are the basic things that will be asked in your objective questions or in a board examination. If you are appearing in JEE, so in JEE mains, question can be asked based upon these two formulae, and if you are appearing in medical examination, question can be asked, simple question can be framed on this simple concept. In board examination also question can be framed on this concept. Let's go ahead with the next very interesting topic, that is capillarity. Now capillarity, you must have listened to this term, capillarity, very interesting thing, and you must have observed. Now while doing experiments in chemistry lab, have you ever observed you would have taken a capillary tube which is open from both the ends. Your teacher would have advised you to dip the tube in the solution. You will be seeing that a part would be raised in the capillary tube, and then you would be closing your thumb and bring out the tube and pour in the test tube. You would have observed and you would have actually done all these simple experiments. Now what is capillarity? Capillary, first of all let me tell you what is capillary tube. It's a very small narrow tube thin which is open from both the ends. So first of all, capillary tube, a narrow tube which is open from both the ends. Capillary tube, it's a narrow tube open from both the ends, and it will be having actually a cylindrical cross section within it, so that will be actually hollow portion. Narrow tube open from both the ends, open from or open through both ends, that will be a more better word to signify it, open through both ends. I believe that this would be clear to you about the capillary tube open through both ends. Now next part, capillary tube would be pretty much clear to you. I told you about the cohesive force and adhesive force. I told you about some liquids actually wet a glass surface, some liquids do not wet a glass surface. Water actually wets the glass surface, I told you in the first lecture of this topic. And if you take mercury, mercury will not wet the glass surface. So how the capillarity action actually takes place in the case of water and mercury, let's try to understand. If you take a glass tube and if you take two tumblers, one you fill with water, one you fill with mercury, what you will be observing, let's say I have taken two tumblers. In the two tumblers I have filled one with water and the other with mercury. Let's say I have taken water here and I have taken mercury in the other tumbler. Hope that you can easily understand what we are referring to. Mercury we have taken here. Now what you do, take two capillary tubes and immerse in both the liquids. What you are going to observe, see here, you are going to take two capillary tubes. This is actually water, let me tell you, this is water, and here you have taken mercury, remember. Now what you are going to observe, in the case of water, when you have immersed the capillary tube, once you have, here you have did, and the same capillary tube you have immersed in this mercury solution, or mercury as a liquid, you have immersed in both the cases. Now what will happen, water will actually rise in this capillary tube. So I am going to show you here, water is actually going to rise here and mercury will actually dip down. Mercury will actually come down, and in this part it will not rise, rather it will dip down as shown here. So let me also mark the height of the water column from the free surface. If it's h here, let me show that here the height is h that we are referring to. In one it will rise, in one it will fall. Here we find that there is a rise and here there is a fall in level of mercury in the capillary tube. What is the significance and how can you decide which liquid will rise, which liquid will fall? Let me tell you, if the liquid is going to wet the capillary tube, then it is going to rise. So, first property, I will write the property in a separate way, and in the second one, liquid is not going to wet the glass tube. So, first of all, let me try to show you all how you are going to decide. So, when it rises, so first liquid wets the capillary tube, liquid wets the capillary tube, so it is going to rise based upon the cohesive and adhesive forces. Cohesive and adhesive forces. Now, liquid wets the glass tube, that means adhesive force between liquid and capillary tube will be more compared to cohesive force between the same molecules of the liquid. Second, adhesive force between liquid and glass, between liquid and glass will be greater than cohesive force between liquid molecules. Cohesive force between liquid molecules. This is what we know that should happen in the case of rise. So, I believe that you can simply take down these 2 points. This is the reason, and actually what will happen, the liquid will be actually it will be stuck to the glass surface of the capillary tube and it is going to rise. And I will tell you more about it when I teach you about the angle of contact, but before that note down these 2 points. Now, next thing, what if there is a fall in the level? If there is a fall in the level, then liquid wets the capillary tube. No, it will not wet the capillary tube. So, liquid does not wet the capillary tube. Liquid does not wet capillary tube. First point. Second, adhesive force between the liquid and glass will be less than the cohesive force between the liquid molecules. So, just change here one more point, the inequality sign. It will be less than the cohesive force acting between the molecules of the liquid. So, just change the inequality sign that we are using in the case of fall. Now, how are we going to understand the capillarity? I will tell you that. Prior to that, let me tell you some practical places where you are going to observe the capillarity action. Now, at many places, capillarity is observed in our day-to-day life. First of all, if you have used lamps, kerosene lamps, let's say there's actually a soak paper, or let's say a blotting paper is actually connected as a leaf which actually sucks the oil from beneath, and that is actually due to the capillary action. There are actually very minute spaces and holes through which the fuel, or let's say the kerosene, actually passes to the top part where it will burn and when the flame actually comes. The first part, in kerosene lamp, you will observe the capillarity action. Now, there are many other portions, even in the trees and plants, the liquid rises from soil to the top, that is due to the capillarity action. In trees and plants, the capillarity action takes place, which makes the water rise from the bottom to the top part. Capillarity action takes place even in trees and plants. There are many more places, see even a blotting paper also, if you take liquid, that actually soaks the liquid due to the capillarity action. The blotting paper, okay, this also soaks the liquid due to the capillarity action. Now, if you observe that the pen, the front part of the pen, or let's say the fountain pen if you have used, or let's say the needle, the nib of the pen, is actually sliced from between. That is actually so that it may make the liquid rise through it. So, nib of pen will make the liquid rise through it. That is also due to the capillarity action. There are so many places. Now, see, even in farmers, actually they till the land, they make furrows. Why they do that? not furrows, actually they have to till the land so that the capillaries may be destroyed, so that water may not come up and it may not get evaporated. To save water in the soil, they actually till the land so that water may not come up and water may not evaporate. So all these are applications of capillary tube. I hope that whatever I have said orally also you would have understood if I have not written it separately on the board. Next part. Now, first of all, I told you about the capillarity action. I told you about once liquid wets the surface, it's going to rise. If it is not going to wet the surface, it's going to fall. Now, before understanding capillarity, let me tell you one very important thing, that is angle of contact. Now, angle of contact, have you ever observed the water surface? Water is actually in a concave fashion, that I told you. Now, if I take a glass beaker and let's say water is kept inside, so water will be, its surface will be formed in this way, as I have told you also. In the last class you have seen, I have discussed this portion. Water is formed in this way, it's a concave way. Now, if I actually tell you, if I draw a tangent showing you how the liquid surface is going to make with the glass surface, then the tangent that it will make an angle with the glass, that angle will be termed as the angle of contact. So what I'm going to do, I'm going to draw a tangent. So let me draw a tangent here showing in this fashion. I hope that it will be clear to you all. Or let me show you here. Here also you can see, understand. This is a tangent that I have drawn at this part. Now this tangent is going to make an angle with the glass surface. This angle is the angle of contact, theta. Theta is the angle of contact. Now see, theta is actually acute for this liquid which is actually wetting the glass surface. So what do you do? Take note till here. I'll start from the other end. Take note till here. So I believe that you would have understood what about the angle of contact when the water actually sticks with the glass surface. Now I will also define the angle of contact, but before that, see this in the case of mercury, what happens. If you take mercury and if you try to observe its meniscus, now see, mercury will be actually in a concave fashion. This is actually up the surface of mercury. You will be finding that mercury will actually form its surface in this way. Mercury will be in this way. Now if I draw a tangent at this part, which is actually touching with the glass surface, so if I draw the tangent, it will be along this direction as shown. This will be the tangent. Now the angle which it makes with the glass surface, this will be the angle. Now for mercury, the angle of contact is given here, theta. In this case, it is obtuse. So I believe that you can easily go ahead and define the angle of contact, which will be given as angle of contact in both the cases. Now it is the angle which the tangent of the liquid surface makes with the side walls of the glass container, or you can understand it this way, it is the angle, which the liquid surface, it is the angle which the tangent drawn at the liquid surface, makes with the walls of the container, Hope that the angle of contact things would be clear to you all. Now see here, once again let me tell you, here in the water case it's along this sense, and in the case of mercury it's along this, in this way. Now both can be understood by, if you know the understanding of cohesive force and adhesive force, both can be understood. Now in the water case, the cohesive force between water molecules is less compared to the adhesive force between the water molecule and glass, that is the container wall that is here. So hence you will find that the net force will be somewhere here. What I am going to do, I am going to show you the forces direction so that you will be having a clear idea. So I am going to tell you first of all the cohesive force between water molecules is lesser in magnitude compared to the adhesive force between glass molecules and the water molecule. Now see, the adhesive force between glass molecules and water molecules will be somewhat here. This is adhesive force, and the cohesive force between the water molecules and water molecules will be here. Let me show you with a separate color. This is the cohesive force. Now the net force of this two will be directed here. This is the net force, and we all know that the surface always tries to keep itself perpendicular to the net force, so hence that's why it's formed in this way. Just opposite is the case of convex meniscus, and this is a concave meniscus case. Concave meniscus. You can see how the forces are directed, and that's why we all know surface will be always directed perpendicular to the net force, and that's why it's oriented along this way. Now you all note till here. I'll start from the other end. Note till here. So you would have understood about the case of water and glass, why the angle of contact is in this way. Now let's try to understand the same thing in the case of mercury, why it makes an obtuse angle. Now first of all, here the cohesive force between molecules of mercury is more than the adhesive force between glass molecules and the molecules of the mercury. That is, adhesive force between the glass molecule and the liquid, the molecules of mercury will be less. So see here, the adhesive force will be acting along this direction, and the cohesive force will be acting along this direction. Now the resultant of these two will be directed somewhat here. This will be the resultant F net. Now we all know that the surface tries to align itself perpendicular to the net force, so that's why it's aligned in this way, and that's why a convex meniscus is formed in the case of mercury. Convex meniscus is formed. Angle of contact is obtuse in convex meniscus, angle of contact is acute in the case of concave meniscus. Hope that the angle of contact and the kind of meniscus formed would be clear to you all. Let's go to the next part, trying to understand the capillarity rise and what formula we can draw to actually understand capillary action. I told you about a liquid rises in a capillary tube. So let me draw a tumbler and let me draw a capillary tube. Now we all know that liquid will actually rise in this capillary tube. So let me show you all differently how the liquid surface will look like. This is the liquid surface. I am drawing with this shaded portion the liquid surface and the entire volume of the liquid. Now let us say it has risen up till this end, and I will draw, and let me draw a bit wider section so that I can show you all clearly how you can understand the capillary action. Let me draw the narrow tube in a wider way. Now see, the water will be making a meniscus that will be concave in shape. Water will be making a meniscus that will be concave in shape. Now see, let's say the radius of the tube is given as capital R. This is the radius of the tube, and here we have the water which is contained. Now see here, let's say the height till which it has risen, that height is given as h. The height till which it is risen, that is given as h. Now first of all, let me talk about the weight of the water column that is here. So if I write the weight of water column that is here, that will be given as weight of water column in the capillary tube, that will be given as W, that will be equal to volume into density into gravity. So volume will be given as pi r square h volume into density into gravity. So we got this is the weight of the water column in the capillary tube, pi r square h into rho into g. Next part, now let's see the forces. Now see, due to surface tension, water molecules, this surface, try to see the surface, this will exert a force along this direction. This will exert a force on the glass tube along this direction, and this force per unit length will be equal to S, that is the surface tension of the liquid. Now from Newton's third law, glass will also exert a force on the surface of the water, and this force will be directed along this way. Now see the angle of contact, we all know that angle of contact is theta, this is how it is given here. So this will be also theta, angle of contact. Now if I see the vertical component of force, so vertical component of F will be given as F cos theta. Vertical component of F, this will be equal to F cos theta. And if I write F as the net force that is acting due to the force applied by the glass on the water, that is given as F, that can be written as surface tension into the length. This will be 2 pi r into this length, 2 pi r, because that surface tension multiplied by the length will give you the force. So that will be equal to S into 2 pi r cos theta. This force is acting along the vertical upward direction. Let me show you separately here. This force F cos theta is acting along the vertical upward direction, F cos theta. So you can write F cos theta is equal to S into 2 pi r cos theta, and then you can equate it with the weight of the liquid column, that is water. So equating 1 and 2 we are going to obtain, because why we are equating, the weight is acting along the downward direction. See here, weight is acting along the downward direction, this will be balanced by the force due to the walls of the tube on the water column. So 1 equals to 2, so pi r square h rho g will be equal to 2 pi rs cos theta. Here you can see that pi and pi will be cancelled out, and 1 r will be cancelled out. So I am also cancelling this r, this 1 2 will be cancelled out. And now you can write down the value of h, that can be written as, if I write the value of h here separately, the value of h you can see here, that will come out to be 2s cos theta upon r rho g. 2s cos theta upon r rho g. This is the value of rise in the capillary tube. This is the value of the height that has been risen by the liquid column in the capillary tube, that is 2s cos theta upon r rho g. This will be the height. Now what about the fall in the liquid column in case of mercury? What about the fall? If we talk about the fall, I am just going to rub this diagram. Before that, try to understand the reason has taken place, and the rise in the level from this free surface is given as 2s cos theta upon r rho g, and we have neglected this part. See, we have not considered this part separately, we have only taken this part entire as height h, and we got it. We have not considered this shaded portion, we have not considered this part, the concave part. Need not to worry about that, that's not required also. Now next thing, what if we have the mercury in the column? What if we have mercury, and how will it behave? If we have mercury, we will have that the level actually falls. The level actually falls, and it will fall to a certain depth, and let me call this as this time height h. We all know that theta is angle of contact and it is obtuse. Cos theta, if it is obtuse, that will come out to be negative, that will give us that there is a fall in the liquid column, and that is actually true also. Again the fall will be given by the same formula, 2s cos theta upon r rho g. This is when the meniscus is actually convex. Hope that you have got the formula for both for concave and convex meniscus. Now a thing that will be striking in your mind, what if the height h that you have evaluated in the case of water that was rising, if you have evaluated that is less than the length of the tube, then it's okay, the water will be lying in the tube. What if that is more than the length of the tube? I mean to say you have evaluated h up till some here value. Your tube is up to this length only. If you're thinking that will the water overflow from the capillary tube, no, it will never happen. Water is not going to overflow from the tube. Rather, what will happen, you try to understand, when it's going to come here, it will try to change its meniscus. It will decrease the, actually it will increase the radius. It will increase the radius in such a way that the height will be lower and it will never come out from this capillary tube. So remember, it will never overflow. Never overflow will take place. You take any length tube, never overflow will take place. Remember this point. The radius will be adjusted in such a way that never overflow takes place. I hope that this point is also clear to you all. You must be remembering the formula for capillary rise, that is h equal to 2s cos theta upon r rho g. Here s is surface tension, theta is the angle of contact, r is radius of the capillary tube, rho is the density of liquid, g is the acceleration due to gravity. You can practice problems based upon this, and I will tell you some more concepts in the next class. Till the time you can revise the entire chapter, the chapter has been done. Start practicing problems. We will see more problems in the coming sections. Till the time, do take good care of yourself and start practicing problems. That's it. Wish you all the very best and thank you everyone.